hope it won't be too disorganized because I just put some slides together, and also I'm always told to be less technical, and so maybe for this audience I should have been more technical, so please feel free to ask if you want more details, because I don't really have it in this talk. So the topic is diffusion equations, which is in principle a classical equation that you can also derive from Cardinal-Feynman approach. And these diffusion equations describe the transport of the charge asymmetry that is generated in the bubble wall ahead of the bubble wall into the symmetric phase. And it turns out that these diffusion equations, or the result of this transport, is very sensitive on the particle mass spectrum, which is not really appreciated in formal approaches. And this constitutes order 1 effects that should be included in a systematic calculation of the electroweak value of the baryon asymmetry. And also, I think after working on this, I developed a few ideas or notions on what is required to come up with an improved, with a quantitatively improved prediction for electroweak value chances.
But before you start, it's just this will depend. This just really depends on it's making use of putting certain things into equilibrium and then computing.
Yeah,
this is why. But why are you saying this has never been previously appreciated fully?
People haven't done the parametric study.
Oh, okay. But we always did it for kind of two extreme cases. Like one where basically everything is degenerate, which of course leads to suppression. Yes, if everything is kind of degenerate.
Well, we'll come to this later. In the standard model, you would assume that everything is suppressed by the Weeks-Fallon rate.
But it's strong.
By the Weeks-Fallon rate. Because of strong Fallon effects, but effectively the only reason why it's broken is the Weeks-Fallon, because it's an argument that relies on value number conservation and violates value numbers in the Weeks-Fallon. But we'll come to that later.
Okay.
So yeah, we've heard these kind of things in this talk by Michael on Monday. So there's a cosmic microwave background, and we've seen this. And then there are these acoustic oscillations in the cosmic microwave background, and as Michael already said, that if you add more baryons, then the compressional phases, then this fluid of baryons and photons will become less relativistic, and these compressional phases are more pronounced than the refractional phases. And then what one sees in the cosmic microwave background are these sound waves, and the sound waves have only a finite amount of time to travel from the beginning of time, from the sound horizon to this last scattering surface. And these acoustic oscillations are basically capturing the moment when these sound waves are caught in a different phase, hitting the last scattering surface.
Sorry, what is the sound horizon?
Oh, it's just the distance at the speed of sound from the recombination to the Big Bang, basically.
Oh, okay.
So it's 300,000 years times the speed of sound. And so actually these oscillating fluid is also described by Boltzmann equations, and so this is a very simplistic first guess for these Boltzmann equations, which doesn't contain damping, but the speed of sound basically sets here the dispersion relation, and here's the source term, this dark matter potential, and this is the intrinsic temperature perturbation. And the sound speed is very close to 1 over square root of 3, because the fluid is almost relativistic at the time of recombination. So which means that actually the baryons only make a small fraction out of the fluid. And so here I've solved this equation and also included, besides the intrinsic temperature, you have to include Sachs-Wolf effect and different effects. And you see that if you have no baryons, then these compressional and rarefactional peaks in black are degenerate. But if you add slightly more baryons, then you get a bias. These compressional peaks get enhanced, and the rarefactional peaks in this equation stay the same. And it's only a small fraction of baryons, so it's quite a good coincidence that we can actually observe it in the universe. Because if we had somewhat less, there would be degeneracy between these peaks, and if we had much more baryons, then these rarefactional peaks would die away
So which equations actually solved? The one?
Oh, the one on the previous slides.
Something else.
But besides this intrinsic temperature, so you have intrinsic temperature, you have Sachs-Wolf effect, and also I think different things which give you then the answer.
Okay, so you have that, but psi is given.
That's the
given.
That's the primordial spectrum. Yeah, that's the flat spectrum in gravitational perturbations.
Baryons enter only in BS.
In BS, yeah.
But that's the only place.
Yes, I mean
But
there might be secondary effects.
Why do you get bigger amplitude?
Oh, as I said, this is not the intrinsic temperature is not the final answer. You have to include Sachs-Wolf effect and other things. I mean, I can show you later how I worked it out.
Okay, so you have another equation that you solve.
Not an equation to solve, but the final result will be some combination, and I think there might be theta squares entering and.
I don't see from here immediately why. I see the frequency change, but I don't see the amplitude.
Yes, and this is because of the secondary effects, because what you see is not the intrinsic temperature. So there's also gravitational redshift, which is Sachs-Wolf effect, and other things, because I think Sachs-Wolf and intrinsic temperature actually cancel out, so you have to include a third thing in order to see this. So I think this is the sort of simplest picture where you can start to see something. And yeah, in real life, of course, this is not good enough when you take a computer simulation, it's really fast, and then you can simulate what happens. So in blue I have plotted the observed baryon asymmetry, and in green and in red I have put more or less baryons, and then if you look very closely you also see this frequency shift, so it shifts the second peak because the speed of sound is shifting, and also you see the enhancement. If you have less baryons, the green line, then the affectional peak gets more enhanced. And so, and on the left hand side below L equals 200, there has to be no causal contact at the time of recombination, so there are no oscillations.
So how far would the second peak go up if you switch off the baryons?
I haven't checked it.
Well, this is a 10% effect, but this is the effect of a 10% change.
Yeah, but
it's
you don't
already
see the error
visible.
bars here anymore. So
Pardon me?
You don't see the error bars here anymore on the second peak. So the second peak has very tiny error bars because the statistics is well, and the measurement is good. And so it's really nailed down to better than 10%, as you can see here.
Actually, Michael had in one transparency, actually, precisely. He has also shown how much the peak varies with varying baryon number. If you remember.
Okay, let's.
And then, of course, quite a spectacular result is this agreement between Big Bang nucleosynthesis, which was earlier than the cosmic microwave background observation. And so the big blue areas are the VBN predictions for the baryon asymmetry, taking into account all statistical and systematic errors. And so there's an agreement between both. I mean, this lithium problem, this tangent.
So what is the difference between the yellows and the...
Oh, I mean, the yellow are statistical and blue are systematic errors.
Oh.
And so lithium, I think there's a lot of stellar physics is involved, and so that's why people say the statistical problem, and you can see there's a tangent here, may not be as severe as it seems.
You see, what the people, astronomers do actually, they extend statistical errors such that they reach agreement with CMB.
Yeah, it's wishful thinking.
I don't think this is an overstatement. That's basically what they do.
Okay.
Well, you see this, I think the impressive point is really the one that the deuterium and well, why is there a helium one? I don't. But at least the deuterium one that is quite impressive. Has a small error
but you
bar.
see, the problem with helium is even 5 years ago there were actually two groups that.
No, I'm talking about helium-3.
Yes, but
no, helium-4. I know this has changed.
But there were until a few years ago two groups that quoted results that didn't even overlap.
Yes, but this didn't have anything to do with astronomy, as far as I understand. This was
It had to do with measurement of helium.
anyway.
What do you mean, astronomy?
No, I thought there was also a computational problem somewhere.
No, this was really just measurement of helium-4. The two groups did, and they got very different results.
Oh. Not the main topic here anyway.
No,
Yeah.
sure.
So anyway, it's still the introduction, obviously. So, of course, what we attempt to do is then we would like to have a third set of the prediction from value genesis, what this number is. This may be, of course, over-ambitious, but after all, it's the ultimate goal of this work. And so, no talk on baryon symmetry goes without the Sakharov conditions. And so in the standard model, as Michael also said, we have this chiral anomaly, which violates the axial current, and due to the SU2 sector, so if in the SU2 sector, an instanton couples to this chiral anomaly, and so the instanton violates the baryon number by a discrete unit and by discrete number, or the winding number, and then since all SU2 particles couple to this, and we have 3 generations here, so for each generation and for each SU2 doublet, there's one fermion participating in this transition. And so this means that B plus L changes by 6 units, so 2 for 1 generation. And in the early universe, this indeed appears to happen because before the electroweak phase transition, actually the energy barrier is lower than the temperature, and then these spiral-ons happen fast. Oh yeah, that's what I'm saying here. So there's no exponential suppression in the symmetric phase, and in the broken phase there's an exponential suppression because there's a non-vanishing Higgs vacuum expectation value, and then the barrier becomes larger than the temperature, and you get a Boltzmann suppression. So in essence, in the broken phase, this can be strongly suppressed, whereas in the symmetric phase, it can still be vaguely fast, but on the other hand, this factor becomes small. This will play a somewhat important role later. It's G2 over 4 pi to the 5. Then CP violations, you heard about it already. This doesn't seem to work out in the standard model, at least for this hot electroweak value genesis. Then we need a deviation from equilibrium, and this is solved by or provided by infrared divergencies when you calculate the thermal effective potential, and you have massless bosons in the game. Then an infrared divergence is arising, and when you resum this in infrared divergencies, then you end up with the cubic term. And so this is provided by W bosons, essentially, by the Higgs boson itself. And in supersymmetric models, this can of course be extra singlets or the stop, because you have 3 stops, 3 right-handed stops. This is a good thing. And then I think this is a standard model without a Higgs. So I've actually taken the potential here. And then you see that you can have a situation where you have the symmetric minimum, it becomes a false vacuum as you lower the temperature, and then you can have tunneling from here to here. And however, in the standard model it looks more like this, that you have a smooth rolling of the Higgs field, which appears in a crossover or second order phase transition. And of course you can fix the situation, as I said, by including more light bosonic degrees of freedom. So you can be creative about what you want to add. Then the mechanism, you have, as I said, you need to have this strong, this first order phase transition, and strong first order means that essentially in this broken phase the spiral is frozen out. So first order means that there's a separation, and strong means spiral frees out, and the usual condition is that the Higgs valve is larger than the temperature at this minimum. The temperature is about 100 GeV, or maybe more realistically a bit higher. Supersymmetric models like 120. And so the idea is that you have these bubbles nucleating, as we have been talking about a lot, and then obviously the bubbles, as they expand, basically the fields in the plasma get a kick, or some of the fields get a kick by the Higgs valve, and so they are driven out of equilibrium. And so this provides non-equilibrium conditions. And then in extensions of the standard model, for example, in the MSSM, there may be C and CP violating interactions in the bubble wall. And after all, the effect of this should be that we generate a current in left-handed standard model fermions, and then ahead of the bubble wall, the Weak's Phaleron is waiting for these left-handed fermions, converts it into baryons, and then this asymmetry is recaptured by the bubble wall, and then it's frozen in the bubble wall, which is why we need a strong first-order phase transition. Because if it wasn't strong, it would be washed out again in the bubble wall, in the bubble. And so this work is particularly aiming to describe the process, what happens after the CP asymmetry is generated, and how the stuff is transported, and how it is distributed ahead of the wall. Because obviously you want to transport it quite a distance ahead of the wall, because then you have you give this Phaleron enough time to transfer it into baryons, this chiral asymmetry, or this axial asymmetry. And so this is one of the numerical simulations we've been running. I will explain in a bit more detail how we do this soon. And so this is actually a subset of the densities. So I've summed here Higgs and Higgsino densities, quark and squark densities to make it a bit more tractable. And then also, in principle, we have included all generation of fermions, which you don't see here. And so the picture is that the red line is the Higgs-Higgsino, and in the first place you generate a Higgs and Higgsino density from CP violating interactions, which in our equations we take to be local, so that's a problem in coupling it to other approaches, where the source is non-local or cannot be brought to a local form. And then, so these are the actual charge densities on the vertical axis. And then on the horizontal axis, this is the coordinate with respect to the bubble wall. So see, this is in a frame where the bubble wall is at rest, and I take the bubble wall to be at 0. And so physically what's happening on the right-hand side is that these chiral charges relax, because I have here Q3, which is left-handed top and left-handed bottom, and I have the top. Okay, and
so the wall comes.
So it's moving to the left, yeah, you say.
The wall is moving to the left, yeah.
But why do you have such a big, thick Higgsino source?
No, the
First
source
we
is
do
very
not
localized. So the wall is small. It extends to so it's
No,
20 over T.
I'm asking why is such a long diffusion tail?
So what is the size of the wall?
Because we solved the diffusion equation, you can do it analytically, and
What is the thickness of the
we'll show
wall?
later these analytical tests. I wouldn't really say they're good solutions, but that consistency checks agree with this.
What is the thickness
so
of
I
the
can
wall?
tell
The
you-
units of temperature, this is, as far as I can see, this diffusion length is 1000.
Okay, I tell you what this is. This is D, the diffusion constant, an effective diffusion
Oh,
constant.
this is D over V.
D divided by V.
And V is 0.1.
And V is 0.05 as we take it.
Okay, then I understand.
Yeah.
But what is the
And
thickness
so
of
this
the
is basically what's...
Because you get an enhancement,
Yeah.
1 over V enhancement.
So this is basically very different from the results you have in your papers, because your diffusion solution, after all, looks completely different from this picture.
What is the thickness of the wall, Björn? The wall thickness?
Oh, the wall thickness is, I think,
Like
you
10?
take 20 over T or something.
From which papers?
Hmm?
From which papers?
I think from all papers, among which are yours.
No, I mean with the...
Sorry, then
Oh, you mean the
Thomas.
profile? No, your MSSM paper. I mean, you
With
plot.
Thomas.
Yeah, there's a plot of the Higgsino density
Mhm.
in your paper.
In terms of set, it would mean.
Yes,
it
that's what
looks
I'm.
completely different.
Yeah, I remember. Yeah,
Well,
why
in
don't you
terms of
tell us
set
in
is very
units of
small
set?
yeah?
So how do you explain the difference?
Well, it's your job to explain the difference. I will explain it in your talk.
But could you
Or
tell
how this
us in
exponential
units of
behavior
Z,
comes, yeah?
what is the thickness of the wall in units of in your
Oh,
inverse GV
okay.
ones?
Which would be 0.2. Yeah, that's very small in this picture.
So it's extremely small, you see.
Yeah.
On this. So that is, okay, this is why Thomas has said it's an extremely long tail.
Yeah,
That's where our calculation ends and the other one is starting. I mean, not. After all, we also included the diffusion thing.
Mm-hmm.
I think it was 20 over T.
But you're going to tell us how do you got this picture?
Yeah, I'll tell you. So these are approximate number, I don't have.
Yeah, I guess these are pretty standard numbers, I guess, which everybody is using.
Yeah.
So, but how does this now really fit together? Because you say,
Oh, I'll explain you in a bit how this decay behavior comes about. I mean, I can write it on Blackboard for you, but I also have it on these nice open office slides. So you can just go ahead and explain.
you said this is kind of still the introduction. You
Okay, so I mean, goal of this presentation I'm giving here is to explain you how this comes about. Yeah. So you have all these. In first place, we have the 60 xenosource, and that's what's the point of why I was interrupted. So these densities, Q3 and T, they're axial densities, and then in the broken phase, they, of course, they start to form Dirac fermions because the Higgs wave gets large. Yeah. So especially the third generation quarks get a large vacuum expectation value, and then you can also say you can have scatterings with neutral Higgs bosons which mediate between left-handed and right-handed particles. So you expect that these axial charges stand away. And so I think it's a big theoretical uncertainty or challenge also to calculate these damping rates, which is very related to the calculation of the source, the CPU evaluating source in the series. But anyway, this is responsible for this damping, yeah? Because if you don't have this damping, you would just have a constant solution in the broken phase.
sorry, what do you say? This is related to the generation of a CP asymmetry?
Oh, it's basically the CP even part of the problem.
Yeah, it's a much simpler problem, isn't it?
Well, it's the CP even part, so you have to calculate the CP odd and the CP even, but it's not, I wouldn't say it's much simpler. I mean, it's very much related. I can tell you how we calculated it, or basically the people...
and you couldn't do it in the way in which Tomislav did it?
Well, I haven't
in the
checked
older
this
times?
yet, but I mean, we can't even relate the source from Tomislav yet to this standard diffusion equation stuff.
No, I mean these stuff they did in the 90s.
I don't know how you did it in these papers, it's an
Well,
estimate.
this is MSSM, right?
No, I mean the technique, not
This is
the...
MSSM, right?
Yes, I'm talking about the techniques, not about the actual results. Yeah,
So I will
So
tell you...
the source is the source is
semi-classically, yes.
no, it's not. No, the source is actually
There will be a slide where I talk about the source and the relaxation term, yeah? I mean, really what this talk is about is to understand this diffusion behavior ahead of the ball and how these charges are distributed, yeah? But nonetheless, I will tell you what we assume and what we've taken for these source and relaxation terms, yeah? But I just want to point out where I see where I see the uncertainties in the calculation, yeah? And I think and since these relaxation rates are related to the source rates, I think there's a problem.
We are still talking about Kaplan-Nielsen, but now with a few new insights. Yeah.
Well, I think we first have to see the equations before we continue discussing on
Why
that.
don't you just go ahead and then we'll
discuss later. So this formula, I think also Michael had on his in his talk, but I think it's a very instructive formula. This is namely how this left-handed density, which would be the sum of the left-handed quark and lepton densities, is converted by the Swallow into Gaussian number, which is what we're interested in. And so, as we had last week, since the source is proportional to VW, naively this VW cancels here. Yeah? And then I said this diffusion tail is described by d bar over VW. And so this left-handed density dies because z is negative ahead of the ball. It's suppressed by this factor. And this factor usually is overwhelming the Weeks-Fallon rate. So, which means that at the end of the day, there's an order 1 merit in calculating this diffusion constant accurately. So it's not a square root, it's an order 1. And then, of course...
is it?
Yeah, it's d bar. So
I know, but I mean, if you...
So if you...
Yes, if you integrate this, you get the linear dependence.
Yeah, if you make a better prediction of 50% on your diffusion constant, you get a 50% more accurate result. Yeah. Yeah, and of course, Weeks-Fallon is very important, mostly because of this factor, rather than of this factor. And I guess you understand what this factor here means. It's just the washout, because if you take the ball velocity to 0, then basically this becomes a very small number, because Z is
It
negative.
should be after Z is negative.
Yeah, and then the baryon symmetry will be washed out in the limit of a static ball. Yeah, so that's what this equation is telling us.
So B wall really kind of cancels in the exponent there.
No, it doesn't really cancel. I mean, this number is, so this exponent, this gamma Vs over Vw, is smaller than Vw over d bar.
Björn, may I interrupt you?
Yeah.
You're completely right in saying that from this equation you tend to conclude that the dependence is linear in D.
Yeah.
But you see, this was a long time ago when I did those calculations. But I also remember that the amplitude of the source tends to depend on D.
I have a formula later for the amplitude.
Yeah, and that somehow part of this dependence actually becomes less than linear. But you know, it was a long time ago, and maybe I just got it wrong.
Formula will appear in a couple of
So
slides.
because what I remember is the square root of the dependence.
We can get back to this once I'm there. Okay, we'll just keep it on that. So, and yeah, and this is another numerical simulation. So what I plot here is the spot mass, and I've taken the stop mass to be at 100 GeV, and then I have two different values of tangents beta. And then you see that if you have a small tangents beta of 5, then at the point where the stop mass equals the spot mass, the diagonal symmetry is quenched, so you get 0. Then depending on the spot mass, you actually get a sign change. Yeah. And then for tangents beta equals 15, you get a complete shift of this curve. And I will explain how this comes about. But anyway, this shows that these parameters are important, and it also means I've assumed here a fixed CP violating source. That means that even if you know about your CP violating phases, say you measured in an experiment, unless you do the calculation, it does not directly tell you what the sign of the diagonal symmetries actually is.
And you get a huge result, huh? Can be 60 or
this
so.
is eta b over eta observed.
Yes.
For maximal CP violating phase.
Yeah.
Okay. So this is a factor 20. But then, then you have
so
two possibilities. You can, in the MSSM, you could do it via the Bino or the Vino in the Xeno. This is Chargino or neutralino electrogenesis. Okay. And the CP violating phase between the new term and the soft Vino mass is constrained to order 10 to the minus 2. Yeah. So you would choose this, you would have to scale it down by 10 to the minus 2, and then you actually struggle to get enough.
Yeah, but this is Chargino variations, right?
I think this part is Chargino, but I also have
Neutralino.
Neutralino. And Neutralino, if you choose your particle spectrum carefully, so you make your first generation quarks very heavy, then your first contributions arise at 2 loop, okay? And then the U1Y is smaller than the G2, and also you have 3 Vinos, but only 1 Vino. And so this relaxes. So I think so far the Vino phase is rather comparatively unconstrained, maybe to 10%.
Mm-hmm. So you're trying to say that neutralinos tend to give less constrained baryogens, or more
by measurements of or non-observations of permanent electric dipole moments. Yeah.
But still, you get a much better effect.
dipole moments, there is always possibility of accidents and cancellations.
Well, not really.
No, because you would have to have an additional CP violating phase. So let's say you get it from the A term, and then you can, and these constraints are complementary. So the CP violating phase from the A term gives you a different answer than from the Gauge sector. But then you can measure EDMs for electrons, for neutrons, and Mercury. And so if you put these 3 things together, you have to work very hard to. So it becomes very contrived. So.
But still, I would still say that your result looks much bigger. So if I take the one by Thomas, I get maximally 2 if everything works to my favor. Well, here it seems to get more like 60 or so.
And you don't get any resonant peaks.
Well, but he
Well,
here
this
he
is,
went.
this is Xeno Chargino.
Yes, he just
so the resonance
changes
is not
the binoma.
not
The,
the P of this mask here because
that's
this is
that's the spot and mass, isn't it?
Sorry? The spot mask, yeah.
The spot and mass. Yeah.
But you've chosen it, otherwise with the resonance.
No,
There's no resonance here
I
because
evaluated this at the resonant point, but you see there's no resonance on this axis.
Of course,
You see a
but
resonant
you have evaluated it.
Yeah, this is like the best case scenario. Yeah.
so there's a factor of 30 or so in between
this
the two
approach.
computations.
Factor of 10, I would say.
Well, in the final answer, because again,
Sure, yeah,
I wouldn't
yeah.
directly compare it. Yeah.
Mm.
I'm sorry. And what is the reason of the Kingston?
Oh, these things are okay. As I will explain later, there are some. So essentially, these charges get distributed by closed order by 3-point interactions, inelastic scatterings. Yeah, that you cover interactions, Higgs, left-handed and right-handed quarks. Yeah, and so I think in this case you can even. So what is it here? These are basically kinematic thresholds, yeah, because in a 3-point interaction, one particle has to be heavier than the sum of the other two, yeah. And so we'll come to that later, maybe we'll get more discussion, because this is actually there's room for improvement, because if you only include 3-point, if you do 4-point, it might mellow these things out a bit.
Wall velocity is always 0.05, yeah?
Yeah, that's what we assume here.
So did
For
you check that
completeness.
it's independent from the wall velocity for this range?
I think there will be secondary effects, but I didn't play around with it. Okay, so these are these transport equations, or that's how they look in principle. So in the end, for the whole MSSM, under the assumption that isospin is holds, and so we don't assign different chemical potentials for up-type and down-type left-handed fermions, and we don't assign chemical potentials to W bosons and albinos, then we have, I think, 30-something species which we solve for. So we have 30-something of these coupled diffusion equations. And then we have, so on the left-hand side there's a kinetic term, and this kinetic term is then replaced by a diffusion law. I mean, I will explain these things in more detail on the following slides. Then, important for this, what I'm doing here is also these inelastic scattering rates, which, for example, mediate Xeno to a stop and to a left-handed quark, and of course all other interactions that appear on the standard model. So mostly we have 3-point interactions here. Then there are these relaxation rates. So these relaxation rates break particle number in this network of equation, and they take care that in the broken phase everything goes down to 0 quickly. So they're very important in the game. And then there's the CP violating source. And for our ansatz, so far, by construction it only works with the local CP violating source. So that's why we could plug in the semi-classical force, and we can use the stuff we are actually using. But it would be difficult, or it's yet difficult to connect to your non-local solution for the green function of the Xeno, or of the Chargino.
And this x divided by k is roughly a chemical potential.
Yes, I think I should have a slide where I explain this, because this is very important in my discussion. So x is the charge density, and k is a statistical factor.
Yeah.
And so k is order 1 for 0 mass, and it's exponentially suppressed if the mass becomes larger than the temperature. Yeah.
But you take this source from which paper?
I will explain. It's basically the Cirigliano et al.
But I mean, looking to this Z depends. The wall was in a very small set, yes, and this is where our calculation took place. So it's more or less local, isn't it? I mean, the CP violating source.
Yeah, maybe one can. This would be an ansatz to attack this, because
just to make it to distinguish. I mean, you do a two-step procedure. Yes, first generate this chiral asymmetry, and then you plug it into these
In
equations.
semi-classical, yes. In semi-classical force, it's local. But in this, when you have flavor oscillations, then you really have to look at what really happens with the source within the Chagino sector, because it involves flavor oscillations and how does it relax. So it's essentially non-local physics.
Yeah.
And you cannot really do that way.
Yeah, but maybe what Michael says, maybe one approach might be to make use of the fact that this diffusion length scale is much larger than even this non-local scale. So I could coarse-grain these diffusion equations, and so we can discuss this later.
Yeah.
Yes, but the question is what you take it to be. You know, what is actually the source? And I think the only way you can actually determine the strength of the source is to solve non-local Churchino equations.
Yes, but the extension of the source is the W. This is the wall.
Yes, but the strength of the source you cannot know unless you know. So you cannot just write the local strength of the source there.
So how
because that doesn't take
this?
into account of the fact that, you know, we've heard this morning that there are this off-diagonals that you generate. They actually rapidly oscillate and they get damped and blah blah. All of this physics is not local.
So yeah, you always
cannot
say it's
describe it, but
non-local.
it's-
How does this really look in terms of equations?
Well, you have to write an equation for two coupled Churchinos.
So you say you have the off-diagonals.
Yes,
That's what
two
you call
coupled
non-local.
Churchinos where
That's
all
what-
diagonal density are crucial.
But that's
to
what you
get-
call non-local. It's not that you have
Yes.
integrals or so in there.
No. They are local equations, but the solution is very non-local. You cannot plug in simply the source
Yeah, so
in
basically
a
for-
local. You see, these are the classical diffusion equations. They are by definition local. And the source you cannot calculate by some gradient of something, right? Because
What does the
it's
source
not.
then look like?
No, so the problem is for the Jardinos we get an equation which is similar to this one. But it's not an equation for classical particle densities, but it's for a 2x2 matrix in flavor space, right? So the question is how to couple this thing, which we calculate just in the Giardino sector, to all the other particles. And I mean, one way would be to take into account all the flavor structures of all the particles, but it's really tedious. So of course you would like to avoid that.
Mhm.
And
So you see, you can
But it's
avoid-
local equations
Look.
just for off-diagonal parts of the
What
density
these mass
matrix.
insertion calculations do is they take the source in some mass insertion approximation, but they ignore the fact that there are these flavor oscillations. That's simply, and so and there is this coupling between Churchino flavors, which makes those off-diagonal, well, excites them, etc., right, and kills them at the same time. So,
Okay.
yeah. So all of this physics is not described in the local source.
Mhm. Prima.
Okay. So, yeah, Boltzmann equations, I mean, Boltzmann equations come in many different shapes. And so the classical, most general form is this Liouville equation with a collision term on the right-hand side. So we have this Liouville operator, which describes the phase space evolution, which I didn't write down in this slide, but by Liouville theory, this phase space distribution is then conserved in time. But when you have a collision term, then this phase space volume can be redistributed between different particles. And everything depends here on well, 3 momentum coordinates and on 3 spatial coordinates
Also, the phase space volume can increase.
by creating entropy.
Yes.
Yeah, but I mean, it depends on whether you have causal evolution or not. I mean, if you assume some heat bath, then you
No,
can
but
increase
in the Boltzmann approximation, you can.
Okay, maybe that's true. Yeah. And so, as I said, this depends on the momentum. And one simplification which is intrinsic to this diffusion equation is that one integrates out the momentum, namely over d3k. And note that this is a different simplification from what we were talking about this morning, because then we're just interested in a local number density, and all information on the momentum is lost. But I don't know if we have a slide on this, presumably not, I should have had a slide. But the thing is, we assume that these functions are very close to equilibrium. So in particular, in this approximation of the diffusion equation, you include a chemical potential and a plasma velocity. Yeah. And these are the only unknowns, and otherwise it's parameterized by a Bose-Einstein or Fermi-Dirac distribution. But this simplifies the whole game, of course, a lot, because you don't have to solve you don't have to go to a lattice where you follow the evolution of all different momentum modes, but you basically just have to solve for the chemical potentials and the plasma velocities. The assumption is that you're close to kinetic equilibrium.
And moreover, that the perturbation from equilibrium has certain form.
Yeah. And so in this case, this Boltzmann equation takes the following form, which looks already a lot like the equation I had on this slide. So to a large extent, these equations I'm solving are classical. I mean, sometimes it says in my collaborator these are quantum Boltzmann equations, but the quantum effect really comes just in the source and relaxation terms in my tape, as far as I see it. But you can actually derive all these equations systematically from Cardano-Prime equations, also the classical part, of course. Which I'm trying to indicate here. So we had a very nice talk by Thomas yesterday on the closed type graph formalism, so I don't need to repeat this. And then we have these Schwinger-Dyson equations. And so basically what happens is that well, the Schwinger-Dyson equations are for propagators. And for example, for the scalar, you get a current density when we take the coincidence limit. Yeah. And now taking the coincidence limit is really this means it's equivalent to integrating out the momentum as in the sense we were talking about this morning. So you take really this distribution function, and in a space-dependent problem you would integrate out kz. Or well, you integrate out this momentum with respect to which you have done the Wigner transformation. Also think of it like that. And so you reduce this object, the two-point function, to just the current density by this simplification. And so this is also a problem connected to your approach. So there's non-locality. Well, this essentially is also the non-locality, of course. Yeah.
What does it connect to what?
Oh, this is connected. The simplification is connected to this non-locality. So this simplification also makes it difficult to connect.
I don't think so.
Oh, because you just have an equation for the local current here. But really, your equations are equations for the 2-point function.
No, okay, but we can integrate our results in each degree.
But you haven't integrated out momentum for in your equations. So you solve for a deviation of the distribution function from the equilibrium form. That's what you're solving for.
Exactly.
And so you solve for a momentum distribution. And so this coincidence limit corresponds to integrating out momentum.
Yeah, but that's what we do finally to get the party numbers.
Yes, of course, but this makes it difficult to connect to this diffusion game. Yeah.
If these two operations commute, kind of, can you first solve and then integrate, or do the other way around? They should commute, of course. Right?
No, but I mean, we get a Boltzmann type equation finally. So I mean, of course, you can derive a diffusion equation from that.
Yeah, but it hasn't been done so far. That's what I'm saying.
No, that's exactly what we do. We do it numerically.
Yeah, I'm not sure, but then you don't couple to this. I mean,
No,
basically, you don't get the backscattering.
We can write we can write diffusion equations fine, all just like you do. That's not the difference.
Yeah.
The difference is that these diffusion equations are essentially diffusion equations for two species coupled to each other. I mean, coupled to each other coherently, such that you write this 2x2 matrix.
Mm. So as far as I understood from reading your paper, but it's a while ago, so I might not correctly remember, is that you solve for the Higgs source with phenomenological covariant terms, etc. Then you couple that to the diffusion equations, which you solve.
Yes.
And then the conclusion is that the back reaction on the Higgs is negligible.
That was not the conclusion, that was the assumption, right?
Well, I mean,
And something must have gone wrong there, because the Higgs the back reaction is not negligible, because you really have this diffusion type for the Higgs
okay, but I mean, the difference is that our source is really small to begin with. So
it doesn't matter, because this diffusion tail, it's universal solution in the symmetric phase.
But I mean, back reaction is the reaction of other species on Higgs, right?
Yeah, yeah.
You're saying in your equations you see big back reaction.
Yeah.
In what sense? In the sense of?
Oh, there's equilibration. I mean, you put number density of Higgs
I
somewhere,
believe that.
and then a substantial amount goes into.
But that should not
into
decrease
quarks.
the source.
And this decreases the Higgs. So it has a substantial impact on the Higgs density.
okay, but I mean, we are using those equations.
That's not the back reaction.
It's not exactly what you mean.
That's not back reaction, I'm sorry. Back reaction is the process that will, the deviation from equilibrium in other species will hit back the densities in Higgs. That's the back reaction.
Yeah, okay, it's a semantic thing now, but in essence, from your paper, one would conclude that it doesn't matter to his or Higgsino which other particles are around.
Okay. Different question. Do you think the back reactions would make the result larger or smaller?
I think they make it smaller.
Yeah, okay, so.
Yeah, but then again, then you can say who produces the largest number wins because he gets the most conservative constraints on EDMs. So I think this is, of course, I mean, if you take this argument, you might use the optimistic scenarios anyway for doing constraints.
I'm just telling it doesn't, it supports a claim that the main difference is still the source and not how we can
But
Yeah, that's
how to compare now? So your result, so in your last paper, does this also include the semi-classical one?
Yes.
Yeah, but the semi-classical one is.
Yeah, but why then not doing the following? If you.
I mean, with just the semi-classical force, you cannot.
I think because suppose now you plot everything as a function of mu. Yeah, so there is. It looks like that. There's this peak in between, and it seems in this case you can't really the two equations should the two things should give the same.
Yeah, they do.
Yes.
Yeah, but unfortunately it's smaller than 1. And
but you agree in this. Do you agree in this point? When you really when you're away from the resonance.
No. In this point, I mean.
Do the two computations give the same?
I mean, the approach by Chiriniano has no semi-classical force. So in some sense you would expect that the result is 0 if you go away from the resonance. But the result isn't, which is of course also a problem.
But okay, so
it goes to 0, it gets smaller, but it's not really, it's not a resonance, it's a slight enhancement close to the resonance.
But I think also the problem is if you go away from the resonance, it's strictly speaking not numerically applicable anymore. Because it's basically an integrating over the finite width distribution functions. And so I think this you can only do to a certain extent when you're close to the resonance.
Look, we've done phenomenological damping. That was the main weakness in our work. And how precisely things depend away from the resonance, we cannot really claim within factors order 1 that is really correct. But now that you can.
Yeah, I mean. You're on the same page, I guess. So
I don't think so. No, I don't think so.
Both of you say you cannot compute.
I don't think so.
Away from here.
Sure, we can, but in our case, only the semi-classical force would survive.
In your case?
Well, I'm not talking about the source in this talk. I mean,
no, I'm just talking about observers. Yes, this is the final result of the computation.
Yeah. So.
I mean, this information would be hidden in the source in this case, but I mean, everything.
No, we're just comparing now the final result of the computation.
Yeah, but as I said, I mean,
to see if they agree here, then of course it would, because then of course something you could really easily check is how strong is really the resonance. Yes?
No, but those are completely different effects because in our case, away from the resonance, the mixing source vanishes. So it's just a single thing
is that whatever the source, suppose the assumption is that whatever the source is more or less, that this damping stuff will work more or less the same. Yes, if that is the assumption, then I'm just saying if you would match. And then you just see how big is the amplification. For instance, if you compare the size of the peak in the two computations, it's roughly similar. Which enhancements do you guys get in the resonance case?
I mean, we don't get enhancement. We get just suppression when we go away from. Yeah, but it goes like 1 over. I mean, it's like a Pfeiffer.
No, it's a factor of 5.
Yes, depends how far you go away from the resonance. That's really Pfeiffer in our case.
Yeah, and so does it in the Giuliano approach because.
No, it's not a Pfeiffer.
No, it's precisely a Pfeiffer because that's the whole part of their calculation.
No, it's not. Even if you go far outside, you get eventually a suppression by a factor of 2 or 1.5 or something.
Okay, let's continue.
Let's just continue.
Let's continue. Yes.
So anyway, the thing is, if you look at the Schwinger-Dyson equation, in what sense do they give you the Boltzmann equation? Is that when you calculate this for G less, and then you take the coincidence limit and this double derivative, what actually happens is this term, the self-energy, if you do the calculation, you take the imaginary part of this diagram. And the imaginary part of this diagram is, of course, actually the scattering amplitude. And this is how these 3-point interactions come into the game. And for the 4-point interactions, then you would have to go to higher loops, so you have to work harder. And then it really makes sense to say, okay, I would get the same from the Boltzmann equation because at T level this is classical. But what I want to emphasize is just that these classical contributions are in the Cardinal-Klein equations. Okay, this is actually what we were just on about. This is how this group.
What do you have there? QTH?
What's QTH? Oh, this left-handed quark, a top, right-handed top, and a Higgs.
Okay, so what
This is just an example.
No, what typically happens if you go to 2 and write the same plot and cut it,
Yeah.
what you will actually get, if you cut it in the right way, you'll get 2 scattering.
Yeah, 4-point.
Yes, and in such a way that the only difference is that you allow for Higgs to be off shell.
Mm.
And Higgs is your intermediary particle
Yeah.
that mediates between whatever
Yeah, yeah.
quark and
Yeah.
another quarks. And then since this is off shell, you can actually treat it to be in thermal equilibrium basically. So you can just plug in the propagator of Higgs to be in
Sure.
equilibrium.
Yeah.
But the actual calculation of this is not of 2 loop as opposed to 1 loop is not that much
Yeah,
higher.
of course, in the end, you can.
So of course the question is
diagram.
the main difference between 1 and 2 loop is in you making the assumption that Higgs is already on shell after rescatterings, and the question is whether this is reasonable approximation. And in 2 loop you don't make that approximation. You allow for Higgs to be on shell.
Yes, but the 2 loop doesn't include this 1 loop because it's an additional contribution to the effective 2pi effective action. So you have to include both.
I would agree with that.
Well, let's discuss this in private. I think it's good.
No, it's not.
No.
I mean, it's.
Let's discuss this in
Look,
private.
this diagram has this amplitude is 1 order in the coupling constant, and the scattering is 2nd order in the coupling constant. And then you have phase-space suppression. So these guys are really dominating unless they're kinematically suppressed. Yeah, I mean, it also affects calculation of diffusion constants, but we'll get to that later. So anyway, what Vincenzo and Chris and Michael have done is that they look at this diagram here, and then you see what happens. So if the Higgsino and the Vino have a different mass, so again you take the imaginary part, yeah? So the Higgsino has a chemical potential, the Vino has not. So this can kill chemical potentials, this diagram. So it is important for generating chemical potentials if it's CP violating, and it's important for damping if it's CP conserving. And you take the imaginary part of this diagram. And so this scattering, of course, because the wave has no momentum, is only allowed if both have the same mass, the Higgsino and the Vino. Okay? And so if you take the Higgsino and the Vino mass to be identical and you take the zero-width approximation, you actually get divergence. If you take the zero-width approximation and you take the Higgsino different from the Vino mass, you get 0. But as soon as you include a thermal width, then you get a final answer. Okay? So that's what they do.
But is the Higgs wave really constant?
No, it's V of x and V of y. Okay? So we have to account for
So in
different
principle you
Higgs
can have a momentum transfer.
because the
and
CP violating part crucially depends on the fact that V of x is different from V of y because it depends on the derivative of V.
I don't see why I get an infinite result because
No,
if the two have the same.
No. You look at the imaginary part of this diagram. So you cut it in the Vino line. So it's basically a 3-body interaction where the V does carry no momentum. Okay. And in the case where you have 0 width, and then you multiply 2 delta functions.
It's a pinch angularity, basically.
Look, but I mean, Georg, you know that this takes no account of flavor oscillations inside.
Yeah, I'm not defending it here. I'm just saying that's what we use, and we use it because it gives you a local form for the CP violating source.
Sure, but it's incorrect, strictly speaking.
Yeah, but on the other hand, still you have to.
Okay,
What we need to do, or what somebody needs to do, is to calculate the relaxation of these off-diagonal densities.
Sure, we'll do that.
No, but I mean, the main question here is why are our results so different? And I mean, every criticism you can bring against our formalism would reduce further our results, so it would take us further apart. And this one is clearly a difference which might enhance their result by 1 or 2 orders of magnitude. Just because they will get an alpha from the finite width in the denominator.
Yeah.
Yeah. So I mean, in this sense, it's completely clear where the difference comes from. I mean, it's
okay, fine. It's not the main topic
But you
of
would
this talk.
say normally in quantum physics, if you have a constant background, you cannot absorb any momentum, but that's not clear here. Because if you just in the background of the wall, obviously the wall could absorb some momentum.
Well, the particles are off shell in the plasma. Finite width. That's
No,
what
but still,
does.
even if you get rid of that, because you say you get a divergence because you are coupling to a background which cannot pick up any momentum, but here it can, it seems. Because this is just what happens when you have this process in the background of the wall. Isn't that the same thing which would also kind of transfer momentum to the
these
wall?
particles are plane wave solutions. Yeah. Of course, in real life, you have a wall, and these are not plane waves anymore, and then momentum is not conserved, of course. Yeah.
But couldn't
this whole kinetic theory answers assumes that your quasi-particles live in flat space.
But couldn't that be a bigger term which kills this divergence here?
Maybe. We don't know.
Oh, it's something relatively easy to incorporate that. I don't see that you get an infinite result for that, even if you switch off interactions.
if you find it, then
You don't agree?
no, I mean, as I said yesterday, in principle, I think that everything should be fine. I think.
No, I mean just even if you switch off damping,
Yeah.
because isn't this just the same interaction which slows down the bubble wall?
Yeah, but it's a question of resummation. I mean, there are certain effects which you have to resum to them to get something reasonable. It's like
Why would you need a resummation for that?
it's for example in the double
The equation of motion resums it for you.
Yeah.
So if you solve the equation of motion, rather than
True, but is it necessary to
apparently
get
it
this?
is.
No, the problem is that everything is there are a lot of deltas in Newtonian theory. So I mean, if you get a finite contribution to your dispersion relation, right, it will give you a finite shift in the delta function. But I mean, if you of course expand in this perturbation, you get a lot of delta primes. I mean, it's just not visual mathematics at some point. You have to be really careful how to treat that. And besides, you have to resum to get the same result. So it's not so simple. You know what I mean? If you would shift the dispersion relation, and you would expand the shift to get a delta prime. And so
you know if you have a mass insertions in the propagator, you actually the shifted pole, which is a simple pole, when you write it as mass insertions, become sum of multiple poles that are unshifted to arbitrary order. So you get the end pole.
That's why we resum the propagator.
Once you resum, you reduce this to simple pole again, but just shift it.
Yeah, we don't use some kind of. I mean, if you
No, that's also what you do when you compute the
But when you solve the equation of motion, basically
what you do when you
effectively you're
compute
resumming.
a quantum correctional propagator. Yeah, that's what you always do. You resum it. Okay. I'm not convinced that this.
And the problem, of course, with summation here is delicate because there is a space dependent on the mass. So you cannot just resum it like you usually do.
Okay, but that's certainly what is done. Okay.
Okay. So chemical equilibrium. Of course, we have the Higgs-Zeno in first place, and it has to be mediated to left-handed standard model particles. So the most direct way is this way, but then there can also be other equilibration processes. And then in supersymmetry, there are particles and superparticles, and they can chemically equilibrate through supergauge interactions. Another thing which is nice about these three-body interactions is that actually you can reduce them in all generality when you do the thermal averaging to a one-dimensional integral, which is, you can treat it numerically easily without going to Monte Carlos. But if you have four-body interactions, and your masses of your external particles are comparable to the temperature, then I think you would have to. I mean, you can't really say that one particle is much heavier than the others or whatever. And then I think the only way to do it is to do Monte Carlo integration, and that's why we haven't done it. So these guys are dominant if they're not kinematically suppressed over the four bodies, at least for these chemical equilibration rates, not for the diffusion constants. And they are, you can just evaluate them in terms of a one-dimensional integral for arbitrary masses and temperatures. Yeah, so this is actually a diffusion, and basically we take these constants from this paper, and as I emphasized today and yesterday, in principle you can get there from kinetic theory. And so this would be a T-channel exchange, but there could also be, there's this paper by Arnold, Jaffe and Moore, which I think people already mentioned at this meeting, who's pointed out that there's a larger set of diagrams. In particular, there are T-channel exchange of gluons, which are infrared divergent. And then this is regulated by the, again, by thermal defects. And so this is actually a quite involved calculation, already for the case where you have just QCD, the fundamental fermions. So, and then if you want to go to the Higgs sector, and actually the diffusion constant for the Higgs is very important for this game. So it's actually 100 and this is 300. Okay. So this diffusion constant is actually very important. Then you have to do a way more complicated calculation because you have supersymmetric particles and all can have different masses. And so for each special case you would have to have calculated a larger number of diagrams, and presumably, since you have no separation in mass scales over temperature, you have to do Monte Carlo integration. So I think this would be quite straightforward, but also quite a lot of work. So the question is whether one thinks that it's worth it. So anyway, if one calculates these diagrams and does kinetic theory by allowing for plasma velocity, and then one boosts, makes a Galilei transformation to the wall plane, then this divergence turns into this operator, wall velocity times first spatial derivative minus diffusion constant times second spatial derivative. And that's how, by what we replace the kinetic term, which goes back to Thomas Love's work. And so important is now this diffusion timescale, because within a time t, a charge goes a random walk because the particle gets rescattered. Yeah? And so this random walk, so the distance in the random walk, you know, is given by the square root of the time, and to make it dimensionless, there's a diffusion constant. At the same time, the wall expands a certain time, and if you equate these two, then you get the diffusion timescale, which is d over vw squared. Okay? And so this is the timescale that governs what's happening in front of the wall. So if a particular reaction goes faster than the diffusion timescale, you have to include it. If it goes slower, you can forget about it. Okay.
Unless it's the standard rate.
Yeah. But so this diffusion timescale, we have a vw squared, which is different from this exponential decay behavior. And so actually, this is quite a slow scale. So it turns out that you have to include more interactions than people thought earlier. So here this, when it's a process fast, you have the diffusion timescale and you want to compare. So you have at least to include for consistency all rates that where this gamma over a particular statistical factor k, and remember k can be very small if the mass is high. If this is larger than the diffusion timescale, you should include the gamma is larger than the inverse diffusion timescale, then you should. So when gamma is larger than 0.02 GeV, you should include it in your network of equations that you solve. And then you look at the Yukawa rates of the third generation, and they of course are related to tangents beta. And when you compare to this diffusion timescale, then it turns out that YB is in equilibrium for tangents beta roughly larger than 5, and Y tau is in equilibrium for tangents beta roughly larger than 15. And actually, unfortunately, these are not very sharp transitions. So I will later make a plot of the baryon asymmetry over tangents beta, and it goes quite smoothly, but it changes substantially. So in principle, you would include these third generation Yukawa couplings. And so what people have done before our papers came out, or are still doing, because they don't want to solve all this stuff, it just said the top Yukawa coupling is the only thing which is important, because it's so much larger than the other Yukawa couplings. But again, it's not important how large it is compared to the other Yukawa couplings, but the other couplings will care for equilibrium when they are just larger than, these equilibration rates are larger than the diffusion rate. And so this is all in the old picture. So we have the Higgs-zero decaying into a Q tilde. Also, one has assumed that particles and superparticles have the same chemical potential, and then these left-handed fermions go by Weeks-Faloran into baryons. And so this is what this equation, system of equations we are having looks like. So we have the Higgs-zero in this particular example as the CP violating source. Then in blue there are these interactions mediated by G-genus, for example, with a Vino or a Bino in between these can enforce equal chemical potentials between Higgs-zero and Higgs. So these are there for all particles. Then what is also new is that we have include leptons of the third generation, the tau lepton, and the bottom quark. And then what I haven't mentioned so far, there's the Strong's Faloran, which is a QCD instanton, which mediates between the third generation quarks and the quarks of the first two generations. But then the Yukawa couplings, they are so small that only the gauge interactions play a role. And then finally, all the left-handed guys feed into the barium number. All the left-handed fermions, not the squarks. So you need to equilibrate this whole system, or check to which extent it equilibrates to make a prediction.
So what is the minimum number of changes that you have to make in order to get from any 2 points on this graph?
Yeah, we haven't checked that, but maybe an extra paper. So we're writing many papers on this. So why do these particle masses matter? So the most famous example is this argument, which is also known as Shaposhnikov suppression, citation here. So there's the Strong's Faloran. What the Strong's Faloran does, it wants to damp away the axial quark charges. So the left-handed chemical potentials minus the right-handed are zero if this thing is fast. Okay.
Well, I thought it was Thomas Dine paper.
I think it's mentioned in a paper by Hewitt and Nelson, and then
Before.
No, the first one is Judici and Shaposhnikov. Yeah.
Really?
Yeah.
and
With Judici, yes.
Which year? You don't know.
90, around 1990, 91.
Okay, because
Maybe
the other paper
92.
was either 91 92, yeah. Which I think was independent, but maybe they didn't know about Shaposhnikov one.
Could also be 92 or so.
so then, on the other hand, the Weeks Faloran is slow because it's suppressed as alpha weak to the 5th power. So it's not an equilibrium on diffusion timescale. And this means that barium number is approximately conserved. So sort of you have the equation that I should use a different. So let's say the left-handed plus the right-handed quarks are zero, because this means that barium number is zero. On the other hand, you have mu q left minus mu q right is zero because of the Strong's Faloran. Okay. And then, of course, if these are proportional, then you get only a trivial solution. Yeah. So if KL equals KR, KQL equals KQR, and you know that QLR is proportional to KQLR times mu QLR, okay, then we predict that mu QL is zero. So this is the Shaposhnikov suppression. And of course you can get around this by just changing these k factors here. Yeah. And the k factors depend on the particle masses, and since you have quarks here, all you have to do is to choose the left-hand, well, to play around with your soft supersymmetry breaking masses in this quark sector. And that's how you hugely enhance the baryon
The
asymmetry.
K factor, for those people who are not familiar, this is the factor number of degrees of freedom, right? More or less.
Yeah. It's
It's different for fermions.
yeah. But it's 0 temperatures 2 for complex boson, and is it 1 for bifermion, something like that. Yeah. And then it goes exponentially down with if the mass becomes larger than the temperature. Because if you have a large mass, this goes exponentially down, then you have a small physical charge density, still possibly having a large.
So it's roughly speaking, it's the ratio of the particle density you would have at very high temperature,
If there were bosons.
well, up to a factor of 2, divided by
No.
divided by the
No, bosons have infrared populations, which gives them slightly more degrees of freedom. It's
That's
from,
true.
yeah.
But in the particle numbers, in the end, the real particle numbers are really just these k factors
Okay.
times.
Yeah, I think that the boson k factor is of course enhanced because the bosons have this infrared divergence.
Yeah.
So
Yeah, that's what I'm saying.
But
By
it still
three-quarters.
gives, but it still gives you the well, it's this proportion to the particle number density.
Yeah,
So in the end, what is described is really just the Boltzmann suppression of particle numbers if the temperature is much smaller than the mass.
right.
That's what it is in the end. Okay. So you say you can play around with these statistical factors,
But
yes?
playing with the masses. Okay.
Yes.
And yeah, a special case of this argument is that so actually this vanishing of the axial charge is satisfied by the third generations alone if these bottoms are in equilibrium, because this essentially is the axial chemical potential. Also, this one comprises left-handed top and left-handed bottom, and this is right-handed and right-handed. And so this actually means that the strong Phaleron has nothing to feed on to produce first-generation quarks. So another prediction of this stuff is that if the bottoms are in equilibrium, what people haven't taken account before, you don't produce any densities in first-generation quarks. So as strong Phaleron in some sense becomes unimportant. And then you plug this again together with local baryon number conservation, and you get the same result that if the stock mass equals the spot mass and these k factors are identical, then leading order your charge you produce is suppressed. So, oh yeah, and now this analytical solution. So what you do for this analytical solution is basically you assume that all these chemical potentials, or sums of chemical potentials, like this, these q's over k. So for example, for this interaction, q over kq plus h over kh minus t over kt, but these go to 0, yeah? And so the accuracy of this approximation is...
So you assume these rates to be in equilibrium.
The accuracy of this is tau diffusion to the -1 divided by gamma y over k, so to say, yeah? So you say that all these chemical combinations of chemical potential that appear in the diffusion equation are 0, okay?
Which there would be if the interactions in equilibrium.
Yeah. And so this is a good approximation if this is this relation here, this is smaller than 1, okay?
Mm-hmm.
And then you can well, basically get rid of all of these chemical potentials and solve for this left-handed charge density, and you can establish some algebraic relation between this left-handed charge and the Higgs density. So Higgs is now the sum of the Higgs and Higgs 0. And then you see it depends on the k factors, and the first term reflects this fact that if the bottom mass equals the top mass, then you have suppression. And then, but also since left-hand fermions can contribute, for large time in beta, you should also include this term. And since, I mean, typically in the MSSM, you want the right and the top to be very light because you want to get the phase transition, yeah? On the other hand, since the Yukawa coupling of the bottom is not as large as for the top, typically the bottom is heavier than the top, yeah? So this term then, if it's heavier, it's smaller than KT, so this term is typically negative. And this term is always positive, so if you go to large tangents beta, you get the suppression because you get an opposite charge in leptons. So anyway, this is algebraic relation to the Higgs, and then you can take this diffusion equation, calculate your Green's function, and integrate this Green's function over the source to get this amplitude. So this is just the solution in the symmetric phase, which explains the extension of this diffusion tail. And the amplitude is given by integrating over the source here. Yeah? And so this goes back to this question Tomislav had, how important the diffusion is in the exponent, I guess. And the thing is, in the broken phase, this term is completely dominated by gamma bar. And then you get it's the square root of the diffusion constant in the exponent. So it plays a role, I would say.
So I think if you integrate this, you see the way you can integrate is just rescaling y.
How long actually do we plan to continue?
Oh, but actually there's also a contribution where the breaking is, well, it's important in the cancellation here. Anyway, I think it requires further study.
Yeah, I guess we should slowly come
Okay.
to the end.
So, conclude this quickly. There's an empty slide. Then there's comparison numerical versus analytical. So there's in blue this is the Higgsino density, no, this is Higgs density, and this the solid line is what's coming out of the numerics, and the thin line is the analytical approximation, and so it's not that bad. But then if you look at this left-handed fermions, so what we have in green is the lepton density, then you get quite a substantial deviation close to the wall. And this is because these damping terms are larger than the diffusion scales close to the wall. And then actually the analytical solution breaks down a bit. But since you have all these cancellations, this makes the prediction for the baryon asymmetry in the end bad. So this looks better than it actually is when it comes to calculating the baryon asymmetry, because you see close to the wall you have a substantial deviation, but then if you go ahead on diffusion timescales, you reach equilibrium. But anyway, this gives you a nice qualitative understanding at least of what is happening. And so here's an example for particle-superparticle equilibrium. So plot these chemical potentials for the Higgses and the Higgsinos, and for quarks and squarks. And the message is basically that close to the wall you can have a deviation, but then if you go ahead on these diffusion timescales, on these equilibration timescales, then they start to lie on top of each other in the numerical solution. And in the analytical solution, that you would just assume that these are on top of each other all the time.
So you really take the super gauge interactions as finite?
Yeah. Because if they were infinite, they would be lie on top of each other. I mean, you can take this limit even in the code.
Okay.
So this is Yukawa interactions. So these are the sums of the chemical potentials which we expect to cancel. And so this is for large tangents beta. So the down types are in equilibrium here on the right, and the up type is in equilibrium anyway. And then if you go to lower tangents beta, this is the baryon asymmetry. And so for large tangents beta, the leptons contribute, and as I said, there's a cancellation between quarks and leptons contributing to the baryon asymmetry. And if you go to lower tangents beta, you switch off the leptons, and so only the quarks contribute, and so you get an enhancement again. And then if you, this should be 1.5, not 15. And then if you have, that is 1.5. So if you have a small tangents beta, then you see that it doesn't really matter to the top Yukawa interaction. It actually gets enhanced a bit, but then these down-type Yukawa interactions get out of equilibrium. But then you can't really make good analytic predictions because still you have some finite density at the position of the wall, which is set by some scale out here. And you integrate over all the stuff to get your baryon asymmetry. So it's problematic to get analytic predictions for these small tangents beta region. When everything is in equilibrium, you get good analytic predictions, and in this region you are a bit in trouble regarding this. But the numerics is quite reliable if you're happy with these equations you use in the first place. but you may have reason to be not. And yeah, I think I've explained this in detail, so I don't have to go back to this. And now we can also see how this comes about. So I've explained this spot and stop mask quenching. For small tangent-speeder, there's no lepton contribution, and then if we go to large tangent-speeder and switch on the leptons, we get an additional negative contribution, which pushes down the baryon asymmetry, so we can now qualitatively understand these curves. And so this is my last slide. So we already discussed during this talk that we need a connection to mixing scenarios and possibly non-local source terms. So either we have to tame these beasts of these non-local and mixing sources, or we have to go the opposite direction and extend the diffusion equation to take account of this. So it depends on what's easier or what works. I don't know. Then this problem does not only apply to the CP violating sources, but also to the sampling rates in the chiral fermions and the Higgs sector, because they're just the CP conserving counterpart of the CP violating sources. Then account for breakdown of weak isospin and broken phase. I think there's a paper involving Stefan and Former where they studied this, but I couldn't really resolve it. I didn't have the time to look here into it again. But you didn't discuss it at least in that much detail. Read it, so I couldn't really connect or see whether it's directly comparable. Maybe we could discuss it. Then there may be a merit in re-evaluating the diffusion constants, because there's this paper by Moore and Arnold and Yaffe, which do it for the quarks. But really, the most important thing is the weak interaction sector, of course. And there, I mean, this is at best correct by dimensional analysis. I think that's fair to say.
Yeah, there was 0.1 in front. I remember it's some 0.1, 0.2, and things like that.
Yeah. And then, of course, in this region where you have kinematic blocking. So, for example, if you take your, I mean, this is actually a good example because your Higgs is approximately massless at the point of the phase transition, or it is very light. And these quarks have a 50 GeV of mass, so this would be kinematically suppressed. And so you would have to, what you have to do is you have to calculate this diagram with finite width, and then at the same order you have to also calculate the four-body interaction. So you have to do two things, and they contribute at the same order. And so it would also be of merit to calculate these inelastic four-body rates. But I mean, these points are, so these first points are conceptually interesting. These points here are conceptually not very interesting, but it's a lot of work, but it's straightforward, so depending on whether somebody wants to do it. Anyway, that's it.
Okay, thanks very much.